there?
Okay.
Okay. It's great to welcome Al, who's going to tell us about spin 1/2 from color and a little more. So you can begin, Al.
Okay. I thought I will start with a little story, little history. Okay. Where did this problem start? Okay. It started with Wigner in 1938 paper, when he analyzed the representations of the Poincare group, and he found that for positive energy representations, massless particles, there is a representation where the stability group is the E2 group with infinite dimensional unitary representations. Okay. He found it, but he left it there. And as time progressed, there was a certain amount of work, people trying to do work in trying to find a covariant quantum field for this field. Okay. There were many attempts at this direction, and they failed. They could not find a covariant quantum field for this massless particle. A massless particle with E2 as a stability group, infinite dimensional. Okay. There is nothing physically wrong with that, but one could not find a covariant quantum field in right interactions. Okay. Then came a paper, a remarkable paper by Ingvarsson, who proved that there is no such covariant quantum field. Okay. And the crucial point there is, to find a covariant quantum field, some of you may know, one needs the embedding of the little group of the representation into a finite dimensional representation of SL2C. And that simply does not exist. Okay? There is no such thing as embedding E2 in a finite dimensional representation of SL2C. It has lying there. And then much later, I think it was Bert Schroer who found out that there are a more general class of quantum fields, which he called string localized fields, which you'll see examples of it as we keep going. And they will cover this situation also, okay? That the string localized fields may be capable of representing E2 fields. And Jens Mund in the SUSY fora and other people, including Pepin Gracia-Bondia, they wrote papers on this subject. Okay? Now, what is happening is, later it was found out that this construction of string localized quantum fields, which we will see, are of a much more general character and can be applied to any gauge theory that one can imagine. Okay? It is a universal construction. And furthermore, this construction has the property that it works, doesn't require indefinite metric at all, doesn't require BRST or all that junk there. And it works on a proper Hilbert space, and also gives the dressing of the particle by infrared cloud. Okay? So it actually gives a very nice interpretation of how this dressing happens by infrared cloud of massless particles. Okay? So this is happening. I think again, Bert Schroer was a crucial person who did it. And now what is happening? There is some noise coming from somewhere. Okay. Now what is happening is, I would say, a collaboration, a number of people coming from Hamburg. You've had even the names. Okay. Certainly Hamburg is involved. Berlin is involved. Rio, where Bert Schroer is there. SUSY fora, where Mund is there. Okay. And Saragossa, our friend, Fedele's friend, my friend also, Gracia-Bondia, they are all involved. And it is my judgment that there is a sea change happening, okay, in the understanding of quantum field theory in the infrared regime. A lot of new effects are happening, and they are not speculative answers at all. They are proofs. For example, it has been said for a long time now by people like Froelich, Morchio, and Strucki and others, that Lorentz invariance is broken in QED. Now we understand, and there was some confusion. There were Strominger was claiming that that is not true. In my opinion, there is no doubt that Lorentz invariance is broken by QED, by infrared cloud. QCD also the same thing happens. And QCD in further thing that happens is the color is also broken. Okay? That can be understood simply in many ways. And
sorry, but in QCD there are no infrared. There are no.
QCD also has
there are no infrared modes in QCD.
Who is thinking danger?
Yeah, there are no infrared modes in QCD.
There is this whole analysis does not take into account color confinement. Okay.
Okay, you're not. It's unquantized. It's a
we
classical.
Don't know. I mean that we do not know, but at the simple level, I mean the level of quantum field theory before this color, we don't know that there is color confinement or not. So that this analysis does not address that issue. Okay, so we'll come to that. Why? Let me say, we will see that the definition of any quantum field theory depends on the state you choose. Okay, and they dramatically change the representation theory of the algebra of observables, quite dramatically, not in a mathematical sense. Physically, it changes, and here the particular stage we are choosing does, which is a natural, in my opinion, the natural choice, does break Q's color. Okay, and it also creates some Gaussian modes, okay, associated to it. So this is the issue which I got involved. I was thinking for a while, okay? And I want to see how it works out in a particular case. I want to examine what happens in the theta vacuum. Okay, okay, it's not moving. Why is it not moving? Can you?
I don't know, but
yeah. Well, if you press Command L, then you can move it with the up and down keys. But if you don't do that, then you have to actually move the bar that is on the right-hand side manually. Yeah.
We see something else now.
Reading untagged.
Oh, you can see, right?
Yeah.
Okay. So this work is coming out by a lot of conversations with these people, Andres, Parameswaran, Sasha Pinzul, Sachin Vaidya, and so forth. And let me state the problem. Okay? So let me start by saying the problem in the simplest way. Okay? We know that in QCD, for example, in the axion phenomenology, there are binding number transformations, and that comes because the third homotopy group of SUN, okay, is the set of integers. Okay? So there are binding number transformations in the gauge group G, okay, where n is an integer, and if UG, for example, is the operator for binding number 1, it is claimed that action on the vacuum, theta vacuum, which I label as exponential I theta, is given by this equation. UG exponential I theta is exponential I theta times. This is a statement. Okay, this is written down. Okay, it is written down in a fairly formal way, and then people get into functional regulars and stuff. Okay, but the questions remain: what is the state exponential I theta? What is it exactly? Okay? In terms of operator algebra, what is it? Forget about functional regulars. How do I write this operator and do calculations on the algebra of observables? Okay, and what is UG? What is this operator? You are writing this UG. What is this UG? I want to address these two issues. Okay? So let me see how it goes. The answer to the first part is easy. Okay? It is given by the, I would call Chern-Simons twisted vacuum. Okay? So it is exponential I theta. It is given by this integral acting on the vacuum. But Ka is this Chern-Simons term, and it acts on the vacuum. Okay? So this is a quantum state. Okay? Notice that there is no problem of normalization. At least formally, there is no problem of normalization. Okay? And one can easily see that for this state, if I make a gauge transformation, so AG is GDG inverse, one knows that the gauge transform K transforms by the winding number or the transformation G. So this state transforms by exponential I theta times an integer n, where the integer is given by this particular Poincare number of the gauge transformation. Yep. But what is this UG which does this job? Okay, so we want a UG, which we want a UG which has the property that UGA, UG inverse, G covariant derivative, G inverse. What is this operator UG? What is it explicitly in terms of the quantum fields? Hello, you are all there, no? Hello?
We are here, yes. We're being side. We are paying attention, Bal. We're paying attention.
You can hear me, right? So
yes, we can, yeah.
Okay.
Me too.
So let me go and see what happens. Okay. So for finding this UG, we turn to Gauss law. The Gauss law is typically written as covariant derivative E plus the current density acting on the vacuum is 0. This is how Dirac, for example, would write. But this is not a very good way of writing it. Okay. We know already well in another context. Okay, if one of you have looked at elliptic operators on a manifold, Sobolev, there is a weak solution of elliptic operators. So people don't write, these are operator value distributions. Okay, so it's better to write this after partial integration. So we choose a Lie algebra value test function chi. Okay, so chi is a Lie algebra value ordinary classical function, but Lie algebra value, which goes to 0 at infinity. Okay? Then we write this equation up in this way. Okay, so we partially integrate it and write like this. Okay? So in this case, because I have chosen chi to go to 0 at infinity, at least classically, these two equations are equivalent. But I want to write this like I would like to write the Gauss law in this fashion. So this operator here is what I call Q of psi. Okay? So this is the generator of the gauge transformation with small gauge transformations which vanish on the quantum state. Yeah? Okay. Now one checks immediately that Q psi generates gauge transformations. Okay? That is quite easy. Okay? Now the issue is what choice of chi do I do so that this Q psi, when exponentiated, generates a Poincare number 1 transformation. Okay? That is the issue. Okay? So let me try the following. Choose a test function. H depends on the vector x, which is tau Pauli matrix tau dot x hat acting on a function of r. Okay, and for h hat I choose at the origin 0, and at infinity I choose it to be pi. Okay, so that's a particular test function I choose. Okay. Okay. Now let me see what it does to a colored field. Okay. A finite transformation will be given by the conjugation of psi in this way. So I expand this equation out in a power series, okay, and evaluate it term by term, and you see that this is equal, the right hand side is equal to this expression here. So, but I can sum up the series and you get this. So this exponential I tau dot x at h of r, and let me call it g of h. Okay, so it depends on this choice of h, and we can this can be evaluated explicitly because tau dot x hat squared is 1, and you find that g of h is exactly the Skyrmion configuration. Okay, nothing more than the Skyrmion configuration. And since I have chosen h hat to be 0 at the origin and pi at infinity, yeah, g of pi at infinity is -1. Okay, so it goes from 1 at the origin. This g goes from 1 at the origin to -1 at infinity, and it has Poincare number 1. This is a standard Skyrmion configuration. Okay, but this configuration is not in the Gauss law group. Okay, because this h I wrote down does not vanish at infinity. The test function which comes in the Gauss law, which vanishes in the quantum state, has the test function goes to 0, but that is not the case here. Okay, so this is what people in the literature call large gauge, an example of a large gauge transformation. And this U of G is exponential IQH. So this is a gauge transformation but not a small gauge transformation, but because of locality, which there is a small argument, one shows that these observables commute to this UG. Okay? All observables, all the algebra observables commute to this UG. Okay? Okay? Now, there are many such operators I can write down. Not only H, but I can choose other test functions not vanishing at infinity. And the set of such operators not vanishing at infinity, it is called as, we call it the sky group. Okay? Following Abhay Ashkekar's SPI group, spatial infinity group, we call it the sky group, and it was introduced by Sachin and I long ago in 1300, in this archive. Okay? So we had discussed it there, but now I want to look at it more. Okay? It is notice that this object here, this Q of H I am writing, G of H, I told you that all observables must commute to this, okay? Because it is a gauge transformation. So local observables will not know what is happening at infinity and they will commute. But this operator is very strange because this G of H, you notice, couples X hat with this SU2 2x2 matrix, okay, which comes in the definition of, for example, the connection in the Chern-Simons term. So standard rotations, say orbital rotations, will only rotate X hat. It will not rotate tau, with the result that the standard Poincare group, okay, with spin 0 integral spin representations, will not leave this G invariant. Okay? So it cannot be, standard Lorentz group cannot be implemented in this particular, in the particular topological sector where this Q of H, there is Weinstein number 1. Okay? One cannot implement it because the super selection operator changes. Okay? Okay? So what do I do? Okay? So the conclusion is that the standard Poincare group cannot be implemented on the theta vacuum and this folium. Folium is all states you get by applying polynomials to the observables. Okay? So one would say the technical language that they are all the Lorentz group is spontaneously broken. Okay? How do I fix this? Well, one can do this phenomenon, by the way, happened long ago in papers by Hasenfratz et al. Okay? And also by Jackiw and Rebbi while discussing non-abelian magnetic monopoles. And what happens is that the angular momentum operator will change by taking the standard orbital angular momentum by adding a bit of gauge transformation. So this is like a global gauge transformation, tau I over 2 times unit matrix. Okay? This is a constant function, and you add it. So this object also rotates the taus, and this combined operator will definitely will commute to this gauge transformation I am making. Okay? So this operator is augmented by this color transformation, and this operator can be implemented in the theta sector. Okay, there is no problem with that. Okay, but the spin representations of this.
Sorry, Paul, I don't understand your Q here. You defined it as an integral over all space, but it looks like Q diverges.
No, because why should it?
Well, the way you defined it was an integral over all space of something which had this xi in it.
So,
but now xi is constant over space, so that's a divergent volume divergence.
It is multiply. I understand. Let me go back. The definition of Q. Okay, there is an operator. This is a test. You are talking about the test function, but it is multiplied by an operator. For example, here there is an operator. Okay, so when I write tau I over 2 here for the cascade, it is simply the global transformation. J0 is a current density, and it's a global transformation because I chosen chi to be a constant, which corresponding to tau I over 2. Okay, so there is no whether this object diverges or not depends on the quantum state. Okay? I mean, these are operators, so we don't know what it is. Okay? Unless we take expectation values, Depending on the quantum state, it may diverge. That will mean that the quantum state is not in the domain of this operator, or it may not. But in this particular case, it simply rotates the taus. Okay? It's a global transformation. So standard color transformation corresponding to SU2. Okay. So
Okay.
Okay. So I have to do. They can be implemented. So they can. This can. So what has happened is that the rotation generators have changed. Okay. So if for example, if I do 2 pi rotation, you'll get -1 with this operator. Okay. On the quantum states, you'll get -1. So the theta states have half integral angular momentum when I'm looking at least for SU2 as my gauge group. Okay. I'm doing SU2 as a gauge group because I have greater control over it. Okay. So the theta states have half integral angular momentum. Okay. Now, what about the full Poincare group? Okay. Can I implement the full Poincare group or just rotations? The answer is so. As here I am acknowledging that this is not new. This phenomenon was known as spin from isospin, discovered long ago by Hasenfratz and Hooft, okay, and by Jackiw and Rebbi. And even, I suppose, around the same time or before, a similar phenomenon was found in quantum gravity for quantum geons by Friedman and Raphael Sopkin. Okay? So they titled it as spin half from gravity. Okay? I think this is a remarkable result. Okay? One gets spin half without spin half. Okay, feels acting on the Chern-Simons twisted vacuum. Okay. By the way, I should say that this phenomenon also occurs in fuzzy physics, and I gave the reference. It is in our book. So it comes from the properties of projective modules, which one has to construct to discuss instantrons, and you find the same phenomenon there. Yeah. Okay. Now let me come back to this one minute. Okay. So what about the boost generators? We can do that also. Okay. We put SL2C has a finite dimensional representation where the generators are tau I over 2 and I times tau I over 2. So I just change the standard boost with this operator and they will fulfill the Poincare algebra, okay, the Lorentz algebra. Okay. So what I'm getting is a representation or the Majorana, I'm getting is a Majorana representation or the Poincare group. So the claim is that the theta vacuum I'm dealing with is giving a Majorana representation of the quantum group. Okay. Now I want to say just one word, but before I do that, okay, first let me say that the Majorana field breaks parity. Okay. As we know, just like the Chern-Simons twist, so it is coherent. Okay? I think here I don't know enough that the axion phenomenology, if built on the theta sector, will be affected by this new Poincare representation. Okay? I'm pretty sure. The only calculation I know due to Aurelia Townsend and Takahashi long ago, and also by here in Syracuse, okay, there was some work by Joe Schechter. Okay. They deal with the sector as though it were spin zero. They write effective Lagrangians, but there is no hint of an internal symmetry, of something like a gauge symmetry. There, I could not, I have worked on it with Amilcar, but I could not modify it to take into account this new phenomenon. Okay? I don't know how to generalize that approach to this particular situation. Okay? But the main thing is that the choice of the quantum state determines the representations of observables. One cannot talk about observables and quantum states separately. It depends upon the particular quantum state you choose. And this is already clear from the GNS construction, okay, which gives you the representation of the quantum state on the Hilbert space. And it can lead to many inequivalent representations. Okay? And this is well known for electrodynamics. In fact, there are many different superselection rules, sectors. In fact, for QED, there are in fact an uncountably many such states. Okay? Okay. And they are created by infrared effects, as is well known. Okay? I think it goes back to work of Tom Kibble, and later a lot of people, Detlef Buchholz, then Ingvarsson, many people have worked on this. And at the level of QED, they are, I would say, they have the status of proofs. Okay? Okay. So that means that in the infrared regime, all this is happening at infinity. Okay? There are infinitely many descriptions of QED. Okay? Okay? And in QED, I'll just show you, they break Lorentz invariance. Okay? Okay? And QCD, as I said, okay, they also break color transformations. I'll give Sachin, we pointed it out long ago, and then I had a paper using some technology coming from Ropstroff, okay, who used Weil algebra. Then also Parameshwar and I did a paper. Okay, okay, I'll come back to this. Okay, and by the way, I don't know how to. How to account for color confinement. I don't know how that fits this framework. Okay? How to fit it in this. One thing I can remark is that it is possible. Yeah, you see, you can ask, how does a spin half object arise from a Chern-Simons twist in the vacuum? Okay? Yeah. You don't see any spin half. Okay? Of course, Chern-Simons is acting on a spin half representation of SU2 because the connection fields are SU2 valued, and you get a tensor product of the standard Fock space and the spin half representation of SU2. And how does it? How does one recover a Majorana field from this? Okay? Yesterday, and I have to check it again, I found a projection operator. So one can construct projection operator which will take this tensor product state and apply a projection operator which will couple the two parts, namely the one without any spin half, the spin half are together, and produce a projective module on which this Q of theta I wrote down acts nicely. Okay? And the rotations also act with these extra terms that I have written down. So once you have it, I suppose one can use induced representations and construct the full Majorana field. Okay? So this is work. Well, I have to check some simple algebra, but it looks correct. Okay? So I think that the property of spin half is already implicit in the Chern-Simons twisted by spin half. Okay? The SU2, when the connection form is Lie algebra valued in SU2. Okay? Now, if you ask what happens for SU3 or higher representations, I should say that I don't quite know. Okay, that is, if higher groups, exactly how it is twisted by this projection operator, I don't know. I mean, because it's too new, but I believe that there must be a way. Okay, so what very much like this fermion states can be promoted to dibaryon states, okay, which will act on three flavors, okay, which I did with Fedele here. There is, I think, there should be a way, but let me say, I don't know. Okay? I have to work on it. Now, let me go back to the sky group. Okay? In general, this cascade sky, the generators of cascade sky have, as xr goes to infinity, it goes to some angle dependent limits. Okay? Okay? And this gives you the group which we wrote down. Now, but and there is a super selection sector which is defined by such a chi. Now, each super selection sector is labeled by, just like a standard quantum theory, a complete commute set of operators. Okay? And we are evaluating those quantum operators on some quantum states. Okay? So we can ask, what are the states which will excite these this chi things, or say elements of the sky group. Okay. So let me first look at the abelian case of QED. Okay. The abelian case of QED has been, I would say, quite thoroughly discussed from this point of view in a recent paper by Mund, Rehren and Schroer. Okay. And I will give a simple presentation of what they have done. So let me consider let me say something. It is my opinion that gauge theories, as we know it, is getting turned upside down. Okay. The standard manipulations one does with gauge theories, it seems, are literally turned upside down because of these infrared effects. The standard arguments simply don't work. Okay? So this, I think, is I should say revolutionary, but it's a profound change that is happening in the theory of gauge fields. And it seems to me.
Sorry, Paul, can you say what standard one argument you have in mind? Just one.
We write Lagrangians and we write BRST and manipulate perturbatively and so forth. No, it seems that at least in QED and very likely in QCD, they don't work because of infrared effects. Okay? None of the operators you write on exist, okay, as operators on the quantum states defined in the theory, and some new understanding has to be brought in. Okay? I think this is happening right now. Okay, and I want to emphasize this fact too.
But just to be clear, if I set theta to 0, they do work.
Which one?
If the theta vacuum is 0, if we stick to the 0 sector, theta sector, they do work.
Unfortunately, it will not work. The example of the example I took for theta sector was because it was very vivid. You get spin half. Okay, but in QED you don't have a theta sector, but effects because of infrared dressing are very dramatic. Okay? And it was known, I think, to Tom Kibble. Okay? And people from, and certainly it was known to Rohrlich, Frohlich, and Morkios-Strocki, and people following them. Okay? They were certainly known, and it's certainly known, it was known to Bert Schroer. Okay? So you don't need the theta sector. Theta sector is showing that if I change the superselection sector, the physics of the theory totally changes. Okay? Can totally change. One cannot talk about observables and states separately in gauge theories, which is what people do. For example, in doing BRST, I don't think it's correct. Okay? We have to learn some new language. Language may be unfamiliar, it may involve operator algebras, but that's okay. Okay? So let me look at the photon field. Okay? And let me look at it in the Feynman gauge. Feynman gauge, the 2-point function is given by this expression. Okay? Where D is the causal propagator, and I'm looking at just the 2-point function, free fields. The field operators act on an indefinite metric space. Okay? In this expression, it's called the Krein space. Okay? It is a mess. There are the Gauss law. If you look in the Krein space, the divergence of A is not 0. So the Gauss law is not fulfilled. There is an extra term in the Gauss law, for example. Okay? And one has to handle it by going to indefinite metric space, canceling them. There is a whole technology for that. Okay? But what these people do is the following. Let E be a vector, constant vector, where E dot T is negative. Okay? My metric is eta 0, 0 is plus 1. Okay? So E dot T, I think Giorgio likes this metric, I think. Yeah? Whereas in relativity, they prefer the other one. Okay? Now, this E dot T less than 0, it means that this set of E's is a union of de-Sitter spaces. Okay? Yeah. If you go into, say, 2 dimensions, is exactly the Riddler wedge. Okay? So this set of E dot E are negative. Now let me define what they call the Mund, Rehren and Schroer called as the Escort Field, which is coming from Dirac's work. What I'm doing is A lambda, the connection form, x plus et, multiplied by x plus e times some parameter tau, e lambda d tau, integrate from 0 to infinity. Okay. So this phi is like a Feynman, what is it? Path order integral, okay, that we normally use, but in the infinitesimal form. Okay. So this is phi. Okay. And we can ask what is a gauge transformation property of this phi. Okay. And it is very simple. And Dirac knew this. Okay. So under a gauge transformation by q psi, this A will go into A plus D cascade, and you will get two terms, one corresponding to this limit and the other corresponding to the x point. Yep. So if I look at exponential I phi xe, it will create a charge on sky. What I call sky is very far away in the direction E, and it will also create an anti-charge at x. Okay. Again, this is quite, I think, quite well known to Dirac. Okay. So it creates something at x and the anti thing at the spatial infinity. So for the electron field, if I multiply it by exponential iq phi of xe, psi of x under vacuum, okay, this is a vector state which is certainly Gauss law invariant, because the phase that comes from psi is cancelled by the one from phi. Okay, and there's a charged blip in sky along E. Okay, because at infinity it creates a blip and it doesn't go away. Okay? So this infrared field, I want to discuss the infrared field, okay? And it can actually be written as a quantum field. Okay, let me do it for free fields. We just take the standard by Feynman gauge A muse. There is E mu standing here, and I integrate from tau, and you get this expression here, where this k dot t plus is the limit k dot t plus I epsilon going to 0. Okay, so so this object is a plus means is in a distributional sense. Okay? So this is well defined when we do calculations in, for example, perturbation theory. Okay? So this is my phi. Okay? It is actually a good quantum field, and I want to discuss its properties in a minute. Now, the main point is that this object here under gauge transformation creates a blip in the sky along E. Okay, so if I multiply the operator exponential iq chi, okay, which defines the superselection sector on this object here, it will give the eigenvalue corresponding to corresponding to the gauge transformation at the point E at sky infinity. This will give it at the point E prime, because the chi is gauge transforming it. So this will give you the value of the test function chi at E at infinity. This will give it at the point E prime at infinity. So the superselection operator is different in here and here. Okay? So since they are different, they're giving you different superselection sectors. Okay? This one and this one, when E is changed like this, are giving different superselection sectors. So no observable will connect them. So we would expect that they are orthogonal. In fact, they are orthogonal. The calculation is non-trivial, but in Mund et al. Paper, they have explicitly carried out the calculation and find 0. But my argument will say that since the exponential iq chi have different eigenvalues here and here, they have to be orthogonal. The simple way of seeing it, but an actual calculation can be done, and they have done it. It requires some complex variable activity, but they have done it. Okay? So we find that when you change this direction E, which defines for you, if you like, the axial gauge, and you shift it from E to E prime, you are actually changing the superselection sector. Okay? What does it mean? Okay? Suppose I now look at what happens to the Lorentz group action U lambda. What happens to the phi? Well, let me go back to the definition. Okay. See, if I make a Lorentz transformation, it will change this x, okay, this argument x plus e tau, fine. So E will be changed by lambda. Then on E A lambda, there will be a spin matrix acting. Okay? So that will also change this E lambda. So the net result is, okay, that under Lorentz transformation, the lambda, both x and e change. Okay, not only x but also e changes. The direction of the axial gauge changes. So we are not thinking of axial gauge as a fixed t. We are allowing it to fluctuate. Okay, so because it is changing e, it changes the superselection sector, because we just showed before that this changing the e corresponds to changing the superselection sector. So the Lorentz group is changing the superselection sector. Accordingly, Lorentz group is spontaneously broken. Okay? This is a summary of, if you like, much earlier work by many mathematical physicists, like the oft-quoted paper is definitely due to Froelich, Morkio, and Strokey, but I think many people have looked at this problem, okay? Including Detlef Buchholz, okay? Whom I remember talking about this in Dublin. Okay? So this is very remarkable. Lorentz group is broken in QED. Okay? Can I see it? Okay, I'll come to that in a minute. Okay, and the order parameter is broken. Is there an order parameter which is breaking? I would say that this Higgs field or order parameter is this Escort field. Okay? Okay. So this Escort field is a scalar field. It acts as order parameter for its breaking, and it will acquire a vacuum expectation value in these twisted sectors. Okay, I think. Okay, so and the meaning is very clear. I mean, the infrared cloud is so dense that the Lorentz group is shifting it at infinity, and when you shift it, that you are going into the local operators. Okay, are not sensitive to this shifting, and you end up with a new representation of the Poincare group. Okay, okay. Yeah. So,
well, if I understand correctly, what you're saying here is more or less the same as people would say in that the symmetry is broken in the sense that it becomes nonlinearly realized, as in the Higgs phenomenon. Is that what you're saying?
I don't know about nonlinear realization. Okay, nonlinear realization depends. Nonlinear realization does not change it. So that
you said it's in a different representation.
No, it's more like the following. If you take the ferromagnet, okay, this operator that I am talking about is like rotating the direction of the spin at infinity in a ferromagnet. Okay, so if you rotate the spin direction at infinity, the superselection sector for the ferromagnet is changed. No operator will have a non-trivial expectation value between the two sectors. Okay, if the direction of the spin at infinity is changed. Okay, now so you may ask, what are the Gaussian modes? They correspond to fluctuations of spin directions locally without affecting infinity. Okay? So here I would claim here is that the corresponding fluctuations here correspond to fluctuations of this de Sitter string, keeping at infinity fixed. Okay? So the de Sitter string is, I have taken it to be a straight line, but one can imagine that this whole calculation is done when the de Sitter string is not straight line. Okay? None of the calculations are sensitive to this issue. Okay? So I can imagine fluctuating them. Okay? So I can write a string theory for the de Sitter string, but keeping infinity fixed, and they will give some fluctuations. So I can ask, what are the excitations of this de Sitter string? And I think they will correspond to the Gaussian modes that you are talking about. Okay? This part is not, the problem here is, I think this is correct, but I don't know how to write some kind of Hamiltonian for fluctuations of the de Sitter string. There should be some physically motivated way of writing it. This I don't know. Okay? And there are other issues here which I don't I'll mention here. Okay? So let me now, I think this is very important. This result is very important. And let me say, in the context of this problem, that I have been discussing with Manolo, Arshad, and Babar. I think Venus may like. There is a famous selection rule. It's called Landau-Yang selection rule, which says that Z0 cannot go into 2 photons. Okay? Okay. This is a result, okay, which is very celebrated, and it doesn't require quantum field theory at all. It comes purely from Poincare group representations. Okay? It is a proof. The proof is given in a book on group theory, and just take tensor product of 2 photon representations identically with the same helicity, reduce it on the Poincare group, and you find that it doesn't contain the representation corresponding to a massive spin-1 particle. It doesn't contain that at all. Okay? So it's purely a Poincare group representation theory result. Okay? And it has been tested in quantum optics, in nonlinear optics. There have been experiments on this, but in LHC and so on, they have not tested it. When I talk to people, they say that it is covered by too much junk. So they don't look at it. Okay? But what happens here with the infrared cloud is that one can write down in this model, at least one can write down in Hamiltonian involving this infra fields, okay? And let's say a field for the Z mu, okay? Such that this decay goes through. Okay? One can actually write it down and this decay happens. So this I have checked with Manolo, Arshad, and Babar, and it's quite interesting. But the one problem which I'll come back to is what determines the scale of this breaking. So I'll come to that in a minute. So let me say now what happens for the non-abelian gauge groups. Okay? For the non-abelian gauge group, okay, we follow Dirac. Okay? The basic thing that replaces the Wilson line is what I call Vxe. So this is this integral, where I'm integrating along a straight line from x to x plus e infinity. Okay? Okay? By the way, let me say something in this context, which I asked Denjo. The issue is, in quantum gravity, is there a covariantly constant vector E? Okay? Say for a black hole. Okay? I am not aware that it exists anything like that. Okay? For a say for any black hole metric, I don't know what happens with extremal black holes. Okay? But there do exist connection forms, okay, which are covariantly constant up to a gauge transformation. For example, the connection form that occurs in the Palatini formulation of quantum gravity, there is an E that comes, a frame comes. The frame is covariantly constant up to a gauge transformation. So, but I don't know how to adapt that equation to make this axial gauge for quantum gravity. If one can do it, it will be quite interesting because it will create excitations on the surface of the black hole, okay? On the surface of the horizon. Okay, so that will be quite interesting, and I don't know how to do it. Okay? Just a remark, side remark. So I come back to this V, which is written like this, okay? Where by E infinity I mean the limit to infinity taken in the direction E. Okay, and this is the well-known property that under gauge transformation UG, it transforms on the left and on the right. On the right, it transforms with G inverse X. On the left, it transforms with this gauge transformation G, where I approach infinity in the direction E. Okay? So this object here will not commute with the sky group because it is giving G because of the non-abelian nature of this. So let me look at, if psi is a colored field, let me look at this. Okay? This is Gauss law invariant because, as Dirac himself pointed out, because this G inverse is cancelled out by the G from psi. So this is gauge invariant, but under UG, under a gauge transformation, it transfers with this G here. Okay? So since I'm dealing with a non-abelian group, okay, I can make another gauge, I can look at another gauge transformation which doesn't commute with this, or a gauge transformation, another gauge, it doesn't commute with this. Okay? So what happens is that if I take E and E prime, okay, I look at this V, make a gauge, and I look at Vxe and Vxe prime, they transform differently under gauge transformations. So they are orthogonal. They are again, by the previous argument, they are super selected and they are orthogonal. Okay? I have not proved this, but by looking at eigenvalues formally of gauge transformations, which are different for this and this one, same and the operator is formally unitary, you would expect that they are orthogonal. But I would not know, because of this path ordered integral, I would not know how to prove analytically that they are orthogonal. Okay? That will be interesting, but I don't know how to do it. Yeah? So let me say a little bit more before I come to something. Okay? In QED, this phi xc, the Escort field, the derivative. So if you take a mu, the connection, a mu or QED, it couples to j mu as a mu j mu. But this a mu can be written as a term which is completely gauge fixed in terms of f mu nu using the Poincare construction, plus a derivative term d mu phi. So the coupling of this Escort field to the conserved current is through a derivative. Okay? But this current is conserved, with the result that it leads to no scattering. Okay? This Escort field goes away because of this nature of the coupling, because the current is conserved, but it dresses the field. Okay? So it dresses, for example, a charge field by this by this phase. Okay? Okay? So the claim in models is that this dressing completely captures the infrared dressing. And Mund et al., I think, but Schroer gave arguments for this long ago in 1+1. Then now they are elaborating on this much more carefully in the recent paper. Okay? So in my judgment, we can regard this phi as a Higgs field for Lorentz breaking. Okay? Okay? And infrared dressing is completely captured by this dressing, by this interaction. Okay? Now, the question that people ask is, what is the scale of this breaking? Okay? How? What is the scale at which these effects come in? Okay? I don't really know. Okay? The guess would be that if I have a charge field and I look at this thing, okay, the guess would be that effect of phi will come in depending on the correlation function of the two sides, and when they which is determined by the mass of the field. Okay, and when that starts disappearing, the effect of phi should take over. Okay, okay. So I guess that this will determine the scale of the infrared effect. Okay? But I am not sure. However, I told you that for Z0 to 2 gamma, we can get a good control over that scale, because if you look at the standard model, there is this coupling Z not going to 2 gamma, it comes in perturbation theory. Okay? If you do loop diagrams, you see immediately that this vertex is allowed, even in standard model, but this vertex function you're writing as a scale in front, but if you try doing calculations for Z0 to 2 gamma, you get 0. Okay? In other words, it vanishes on shell, okay? But you get an off shell term. Now that scale, okay? Now if I replace everything by Escort fields in that expression, there is a scale in front. It will not vanish because I have introduced Escort fields, and that scale in front should be the scale where Z0 goes to 2 gamma is controlled by. Okay? This I think is plausible, and one can find the scale. I started doing the calculation. It's quite easy actually to estimate. So I can at least give a number. Okay? Whether it can be seen experimentally is a different issue. Okay? And whether they will be interested, I do not know. Okay? By the way, there are other effects. Okay? Let me. What about the Goldstone modes? Okay? I think they are just the vibrations of these digital strings. Okay? How to modulate, I don't know. Okay? It will be very interesting to modulate. Okay? Physically, you can see, because that simply corresponds to fluctuations of the infrared cloud. Okay? So these fluctuations are the ones those excitations are what one would call as Gaussian mode. Keeping everything at infinity fixed, you look at the fluctuations. That's what we would call as Gaussian modes. How to model it, I do not know. Okay? So let me come to my conclusion. What about non-abelian infrafields? Okay? So is there an analog of the Escort field for non-abelian case? Okay? It appears that there is. But here it is, calculations are not accessible to me. I don't know how to do it. But at the level of not worrying about renormalization and so on, if G mu represents the matter current, we know that the J mu is covariantly zero, covariantly constant. It is zero. Okay? Also, if I take this Wilson line acting on J mu, it is gauge invariant for local gauge transformation at X. So I can imagine doing a gauge invariant coupling where I take V, covariant derivative of V inverse, multiply V J mu. Okay, this is clearly gauge invariant. Okay, and this is a possible coupling. I think that this is analog, could be the analog of this coupling I wrote down, this coupling here. Okay, my guess is that this is analog of that coupling. It is certainly gauge invariant for local gauge transformations. Okay. Okay, let me see. It's certainly invariant under local gauge, Gauss law gauge transformations. And because of the fact that J is covariantly constant, I can take out the d mu and write this as total derivative of V times J mu. Okay, because these two V inverse and V cancel, and this will become this when I take the derivatives, because covariant derivative of J is zero. So what happens is, again, at least in the formal arguments one writes down, this interaction will lead to no scattering, okay? Which is certainly what we want. We don't want infrared clouds to lead to new scattering for the charged standard particles, and apparently no, it will not do it. Okay? However, it will dress the particles, and there will be infrared dressing of the particles that should have the effects I have already discussed. Okay? Again, the Lorentz transformation change this E. Okay? So the Lorentz transformations are spontaneously broken. And so is the color group I told before. Okay? So this V is an example of a string localized field. Okay? So I go back. Why is it called string localized field? Okay? Where is it? So it is a Wilson line. Okay? Yeah. Why is it called string localized field? The reason is, if you look at this operator, okay, in quantum field, and if you take another such operator where, say, x prime, e prime, okay, and x prime is space-like to x, and e prime is space-like to e, okay? So the entire line of x is space, so the point at which these lines originate are space-like, and also the lines going to infinity don't cut, they're space-like, then this Vxc and Vx prime, E prime will commute. Okay. But in case this line I am writing down in E is not space-like to the line I am writing in this expression, then they will not commute. So for this reason, the people working on this field have called them as string localized fields. Okay. It's quite reasonable way of talking about it. The string localization idea is coming from here. Okay? So okay. So I have argued that certainly Lorentz transformations are spontaneously broken. Okay? I think that color group is also color group seems broken. There is another argument which is in my paper with Sachin. The argument is very simple. It's because of the non-abelian why color is broken. Because each supersession sector is labeled by a complete set of commuting operators from the color transformations. Okay? Okay? Otherwise, you cannot diagonalize them. Okay? So each colored sector is labeled by complete set of commuting operators. However, color is not abelian. So if I act on this with the color transformation, it will change this complete commuting set. If it changes the complete commuting set, you are falling into another. That activity is not a local transformation. It's not cannot be implemented by local operators. So that activity is spontaneously broken. So we argued in that paper that color must be broken. This was our argument. I think that argument is correct, and I think that they can be made more substantial by analyzing the equations that are emerging here from. I don't know how to put this in the perturbative QCD language or BRST and so on. I don't know. I don't know how they fit in. It appears to me that the standard gauge theory is undergoing a sea change. But people, I think, should take notice of this. So I'll stop here. I am stopped. So if there are
okay, thank you very much, Bal. I will throw the floor open to questions. Again, Brian is going to ask a question. I won't cut in. So go ahead, Brian.
Can you elaborate on what a de Sitter string is?
String, okay. The direction E, okay. The direction E is the direction in. So the string is simply the direction which one imposes the axial gauge. Okay. So that direction can change under Lorentz transform. So if one changes that, so it need not be a straight line. It can be curved, but I think if in a given supercellular sector is tied down at some particular E. Okay? So if you change it locally, you will get excitations, can get excitations, and I claim they correspond to this de Sitter strings. This is my guess. I think that in 1+1, one can actually do the analysis more substantially, because in 1+1, so at infinity, I am attaching a de Sitter space. De Sitter space.
So where did the de Sitter space come into it?
Sorry?
Where did the de Sitter space come into it? I missed that. I assumed we were in Minkowski space.
It's a Minkowski space, but I am taking a family of directions E, okay, and with E dot T less than 0, right? So these are the directions in which I am allowing at infinity. The directions at which I approach infinity. It's like if I take a quantization on a space-like surface, at infinity we attach a 2-sphere. Okay? But on a 2-sphere in 3 dimensions, but on a 2-sphere, Lorentz group doesn't act. So you have to take. So to overcome this problem, and you want a covariant formulation, the calculation is done by Mund et al. And other people to attach a de Sitter space at infinity, and that is simply the direction of the axial string. Okay? So all the set of axial directions constitute a de Sitter string, the de Sitter space at infinity. Am I clear? I don't know.
So this is a 2+1 dimensional de Sitter space. Is it?
No, the directions E dot T is less than 0. So it is a 4-dimensional.
So you have a space-like vector, yeah.
So the fields are now discussed not on a spatial hypersurface, but let us say you're taking Feynman gauge or whatever it is in a covariant gauge. Okay? So, and in the covariant gauge, I am looking at infinity as a space of de Sitter directions. Okay? So, at least the presentation is done. The de Sitter space is put in so that you can act the Lorentz group. Okay? Okay? Then prove all these theorems on spontaneous symmetry breakdown.
See, I think part of the problem, Val, is that de Sitter space has a scale associated with it, and it's not clear where you're introducing that scale.
Scale. Oh. So I said E dot T is less than 0. E dot T is less than 0. So what happens is, so there is a scale. So depending on the value of E dot T, less than 0, you get a particular, so it's a union of de-Sitter spaces. I told at the beginning that what I got here is a union of de-Sitter spaces, not one de-Sitter. So it turns out that the correlation functions you are writing, okay, is scale invariant. So you can choose E dot T equal to -1. It so happens that they are all correlate. The field, the Escort field phi has 0 dimension. It is quite interesting. Okay, so all the correlators you can write for this exponential IQ phi xc are actually conformally scale invariant. In E, if you scale it, they don't change. Okay, so they are dimension 0 fields. So I said here somewhere. Okay? Yeah. So E is a union of de-Sitter spaces. Okay, not one. So it becomes one de-Sitter space only in one space and one time. Okay? Otherwise, it is a certain union. So there is a scale, but the scale does not affect the correlation functions of this de-Sitter field or this Escort fields. It is scale invariant. So one can ask, since you are asking in that direction, can I write a conformal field theory for these phis? Okay? I don't know. Okay? That will be very interesting. And I think that these people are aware of this, but they have not picked it up, at least in the paper I have seen. I want to generalize this to gravity in a black hole metric. Okay? But the problem is to have the coupling of this phi to the should not lead to any scattering dynamics. Otherwise, it's not correct, I think. For that, one checks that this E must be covariantly constant. Okay? But I don't know, so I can write an expression like this, but what is this E? Okay? So maybe A lambda, I can take a trace in E lambda. So
but your E entered as well in your gauge fixing. You've chosen a gauge, which is bothering me. You've chosen
it's not a fixed gauge because
you've chosen the Feynman gauge.
No, this is a starting point, okay, for the phi, but A mu is gauge fixed, but I go away from the gauge fixing when I look at this expression. Okay, this expression here. Okay, so I'm using this expression I am writing explicitly only. I'm not using it. Sorry, I should say I am not using it when I write this expression and the corresponding expression here. Okay. When I try to write this Escort field explicitly, I'm using this Feynman gauge propagator. Maybe there is some problem there, which I have not thought through, and you may be right. I don't know. Okay. I think because I use a mode expansion for the A to write down this phi explicitly, and there may be a problem. Okay, that I have gauge fixed something. I am not sure. Okay, if I'm not sure about this. Okay, so that's a good point. I don't know whether here in writing this expression, I have actually done some gauge fixing. I don't know. Can I change the gauge? But I can change E. Okay, that will be a change of the gauge. Okay? Yeah. So
that suggests that it depends on the gauge.
What depends on the gauge?
Well, phi depends on the gauge, because if changing E changes the gauge changes E, then you are changing phi. So it depends on the gauge.
Yeah, that's the whole point. That changing the phi corresponds to the Escort. So the quantum field I'm writing, this field, when I change E, I change the superselection sector. That's the point, no? That doesn't depend upon it. That depends only on this expression. And
so changing the superselection sector is different to changing the gauge fixing.
No, you take phi xe, okay? Take A mu, take the connection form as a form in QED. Okay. Then write phi by integrating like this. So take any and write this integral. Okay. So that depends on E. Okay. This is a quantum field. I'm integrating it on E lambda. I get this. So then I go and write down this quantum state. Okay. This is a state, vector state on the algebra of observables. This operator, the claim, is that when for E and E prime, there is no local observable which will connect this expression from E to E prime. There is no matrix element of such a quantum state and the one with E prime. Okay? So they are super selected. Until now, I think it is reasonably precise. Okay? Now, the question is whether this expression for phi, where I have used a particular mode expansion for A, is that valid without, suppose I change the mode expansion to some other gauge. Okay? Will it change this phi? I do not know. Okay? I have to check it. Okay? Give me check. One can see what will happen if I take this and add some extra term to the right hand side. What will happen? Okay? I have not done it. Okay? But the fact that E shifting changes supercellular sectors, E is not. You can say it is a gauge. So there is, you are constructing a whole family of gauge fixed axial gauges. So axial gauge itself is fluctuating. Okay? It is not fixed in this model. If I fix the axial gauge, you will be right. But I am not fixing the axial gauge.
But should I not? Would it not be reasonable to average over gauges?
Okay. So if you average over E, which they have discussed also, E itself is it. So if you average over E, which can be done compatibly with locality and other expressions, one will get a mixed state. So it will be a classical state at infinity, where you are averaging over different superselection sectors. So the averaging with test functions in E, compactly supported test functions in E, will actually give you classical states at infinity. This is very interesting because one knows, at least I think it's true, that observations in quantum field theory or quantum physics is possible only if a commutative algebra emerges therefrom, okay, which is reproducing classical behavior. Okay. This point has been made by many people. Hep has papers, and also Lanzmann has written papers eloquently. Here they seem to be emerging naturally. Okay? They're doing anything. Okay? So yes, you can average over E, but this is at infinity you're dealing with are apparently behaving like this state. Apparently, when you average over E at infinity, are apparently behaving like classical probability, classical states on a commutative algebra. So you are right. We can average over it. They discuss it, but that's actually a positive aspect.
But I'm familiar with the treatment of Bogoliubov and Cherkov of those infrared modes, and they use a renormalization group argument. But I think it corresponds to the averaged over that gauge field that they're dealing with.
Okay. I don't know the Bogoliubov-Cherkov argument. I don't know the argument, but I did not see any non-perturbative argument there. These expressions are non-perturbative. Okay?
Yeah, they were trying to use renormalization group to access the non-perturbative.
So they might have similar results. I don't know. Okay?
But there's very little on it, unfortunately.
Sorry?
They have very little on it, just they sketch an argument. That's about all.
When Bogoliubov is involved, one should be careful. He seems to have known everything. Okay? Including BCS. Apparently, BCS was done by him much before. Okay?
I don't know. But, are there other questions? Just I don't want to dominate this.
Yeah.
Just a question regarding what you asked, Dendro. Is averaging over the gauge, does it give you the same result as doing it in a gauge invariant way?
No, it is not. No, it is like, no. It is a mixed state. These states, so if you take two quantum states, okay, let's say, take the best example, take a charged state and a vacuum state. Okay? Now, if you average, I mean, you cannot superpose them, because if you superpose them, there will be no interference. But if you take the density matrices for charged state and density matrix for uncharged state and smear it with some test functions, you will get a smear the whole thing. You will get some mixed state with a classical, which looks like a certain probability of finding one part of the observable, I mean, expectation values for one part of the operators and other for other one. Okay? So you will not get gate fixed. Gate fixing, no. Averaging over supersaturation sectors will give you mixed states, okay? With some entropy associated with it. Entropy, I think, can be calculated. Okay? Again, the Roberto Longo has discussed this issue. Okay? Not in this context, maybe, but definitely he has papers on this, okay? On entropy of mixed states, okay? Relative entropy of mixed states and so forth. He definitely has papers on it, but I have not read those papers. I am aware that they are there. Okay?
Thank you.
Okay.
I think Charles was trying to get in. Are you, Charles?
No, I was having radiotherapy. I only came back from the hospital 5 minutes ago. I just thought I'd see if you're still talking.
Yeah, no problem. Yeah, sorry.
Okay.
Does anyone else want to get in? And I have a question or a comment.
Did you prove anything?
Sorry?
Did you prove anything?
Did I prove anything?
Yeah.
The level of rigor was not up to your standard, Charles.
Oh,
No. I mean, it depends on the level of rigor. Okay? I would say that at the level of rigor of Mund, Rehren and Schroer, I have not proved anything. Okay? At that level, because
I can look at the recording, Bal. I can look at the recording.
The problem is difficult because these are quantum fields. Say, if I do, I have certainly proved things at the level at which many of us operate. Okay? But that is not the level at which these people are operating. They are worried about domains, states, fundamental algebras, and they are very careful. Okay? So at that level, I would not even know how to address the issues. But if you ask me whether I am confident of the statements I am making, I'm confident unless I am proved otherwise. Okay.
Okay.
I am confident. The first statement about the QCD, the theta states being having this 2 pi rotation minus 1, I think it is correct. Okay. But, thing is that very likely, but I'm not sure, the action is taking place at very large distances. I'm not talking about local theory, but very large distances. So in that context, one knows that everything starts becoming classical. Okay? One knows that it's already there in Hepp's old work on observables at infinity and so forth. Okay? So everything becomes classical or looks classical. So I doubt that renormalization will affect these arguments. Okay? But then one has to wait. Okay? The problem has to mature much more. Okay? But what I am sure
renormalization was in the sense of summing up infrared divergences. It was an infrared renormalization, nothing to do with ultraviolet cutoff.
So I don't know how that will affect these arguments. Okay? I don't know. I don't know where infrared renormalization is even discussed. There may be, I don't know the literature. I don't know, I have not seen anybody doing it. Because what I know is that when you move to infinity, the algebra of observables become classical, become more and more commutative. Okay? This was shown in models by Hepp. Okay? And there are similar arguments due to, as I say, Lanzmann. Okay? He has written a whole book on such things. Okay? And people doing a philosophy of physics, they have this Rushe, I think. So they have argued like this. But again, I don't, let me say, I don't have enough confidence in my maths to be absolutely sure. Okay?
I think we will forgive you that level. We will accept that level of rigor now. That's not going to be a problem.
Acceptable level that we are operating.
Yes, exactly.
I'm confident that these statements I make are correct.
Yeah. No, but I think Joost wants to ask a question.
Yes, this is quite a naive question, but so this whole situation is quite similar to what happens, I guess, in Chern-Simons theory. If you consider it on a manifold with a boundary, then there's an anomaly and you have to introduce a sigma model on the boundary to compensate for that. But there, the boundary doesn't have to be actually at infinity. You can put it wherever you like, which of course also makes sense because the theory is fully topological, so it doesn't matter where you put the boundary. But is there a version of what you're doing here where you just introduce a boundary to the space-time manifold, which doesn't necessarily have to be at infinity? You can just put it wherever you like, and then you still have a violation of these symmetries because something non-trivial happens at this boundary.
Yeah. Who is speaking? I can't see the speaker.
Joost.
It's Joost Slingerland from Manus.
Okay. Okay, fine. The question of boundary.
If you want to stop sharing your screen, you can. You will be able to see the speaker.
Let it be there because I may. Okay. The calculations I have presented here involve very small momenta. Okay. The calculation I have presented. Okay. So for very small momenta, okay, presumably that one needs large volumes, okay, large distances. Okay. So the calculation I have presented here seems to require, I shouldn't say manifold without a boundary, but some non-compact direction where momenta becomes small. Okay. However, Chern-Simons on a manifold with the boundary, okay, actually we did the calculation long ago, okay, and you get a conformal field theory at the boundary. Okay.
Right.
Yeah. So in that case, there are other issues, okay, where one should discuss. In particular, if you have a manifold with the boundary, okay, there is an issue of the self-adjoint extensions of the elliptic operators which come in the Chern-Simons term, okay, and that can be, and of course there is a standard argument of anomaly inflow to the boundary, okay, which is cancelled by something happening at the boundary.
Right. Yeah.
So that will happen, but I don't know how what I have discussed here fits there. So I was thinking about it, hoping that this will give you topological insulators and so on. Okay? This construction of A with an E going to the boundary can be done. Okay? But what implications they have, I do not know. Okay? So one can create H states, the kind you are talking about, by taking a connection from, say, QED and multiplying by E and integrate up to the boundary. You can do that. No? Right. And then allow E to change under, for example, rotations. So if you do that, you'll get a whole family of states at the boundary. Okay? Are these related to the topological insulator bound states? I don't know. That's a very interesting question. And it can be elaborated with some more trouble. Okay? One way or the other, one can get an answer.
I agree that it will be much more complicated here because the theory, of course, is not fully topological like Chern-Simons theory. In Chern-Simons theory, you have the choice to just say, oh, this boundary, I choose a metric so that it's at infinity, and then you have a situation similar to what happens here. But on the other hand, I was thinking here, if you start with the boundary at infinity, like you're currently doing, there should be some kind of flow where you could make the boundary come closer again, and you should have a remnant of your structure that you see here at infinity. But probably it will be more complicated and will depend on the metric now.
See, since you are asking, my impression is, my guess is that at the boundary, this escort fields, they are definitely scale invariant. So if you write correlation functions,
Hmm.
they are invariant under the scaling of E. So you can normalize this E's so that E dot T is -1 because everything is scale invariant. So it looks like you are getting some kind of a conformal field theory at the boundary. What is that conformal field theory, and can I move it to the interior, as you are saying? I don't know. Okay. It seems as understandable problem in QED. QCD may be very complicated, but in QED, yes. There are other questions. The entire gauge fixing, the BB formulation, Battalion because they won't work in this form, in this situation. Okay? Everything is non-perturbative. The moment you start expanding, the effects I am talking about will go. For example, that winding number transformation I wrote down, if you look at it perturbatively, you will see nothing. It is because of the exponential that you get this winding number. Okay? So there are a rich set of topics, okay, which I think will have implications experimentally. I think that is the most important. There are other things. Yeah? I mean, if I make a mistake and they tell the experimentalists, they will find out. No, so we have a possibility of controlling our statements experimentally. That is our hope with the Z0 to 2 gamma and the inverse process. We can find a rate, okay, up to a scale. That I think can be done experimentally in nonlinear optics. Okay? And let's see if they some beam drum experiment or something. But one has to bribe some experimentalists to do this. They won't do it. So yes, there are other things which they have mentioned. Spin statistics fail. They explicitly argue, Mund has, that if you take this infrared dressed fields for space-like separations, they don't, for example, spin half, they don't anti-commute. There is some extra phase that comes, which looks like break group, but it is not the break group. Okay? So spin statistics relation is failing at the level of infrared effects. What are the consequences of that? Spin statistics means that will affect stability of matter. For example, which is a well-known fact that we know that our fingers are mostly empty space. Okay, so why can't I cross one finger through the other one? Why are they not transparent? And one certainly contributing factor is the Pauli principle in spin and statistics. Okay? But the claim now is that that relation is wrong. Okay? It has corrections when you look at the infrared regime. So what happens to spin? The stability of matter and all the calculations of people like Turing and Lieb and so forth. Okay? I don't know. There's a whole lot of physics questions which are underlying these developments. But anyway, my opinion is that quantum field gauge theories are undergoing a sea change. They're getting upturned completely by these people. Okay?
Thank you. Thank you.
Okay.
It's very interesting.
Okay. Do we have other comments or questions? Maybe I will stop the recording and we can
Okay.
Leave it, the recording part of that. Anything that's missing afterwards. So thank you, Bal, for an excellent and inspiring talk. So I will stop the recording.
Okay.
Thank you, Bal.
Yeah.
Okay.
Yeah.
Thanks again. I'm afraid I have to go. So.
Oh yeah, no. That's
Thanks,
you could probably see him now.
Thank you.
Hello.
I mean, the electron has a mass, of course, so it's not clear that that those infrared effects would be as significant there. But the spin statistics that have you thought about the topological argument for spin statistics? What's going wrong?
The topological arguments you are telling me, okay, have been the ones I did with Raphael. I think you were also. Now, they have been, at least I realized later, have been, but there's a mass gap. Okay. Doppler and Hub, they have basically extended those arguments to a quantum field theory. When there is a mass gap, they are rigorous results. Okay? And there is some, what they call exportable endomorphisms. So you can move the algebra from one region to another by certain endomorphisms. Okay? And DHR have proved using this that the spin statistics relation is correct in a fully interacting field. Okay. So it's not it requires some effort to understand it. Okay. They use this Kunz algebras and all kinds of things. Now those arguments, from what I understand from Mund et al., fail in the context we are dealing with, because this Lorentz group failing, these endomorphisms are coming from Lorentz group, okay, and they fail. Okay, concrete. So because of the failure, that those arguments don't apply. Okay, so one has to start all over again. And what do you get for spin statistics? And as of now, I would say it is an open problem. Okay, what is its physical effect? I don't know. Okay. Giorgio,
yes.
Ciao.
Okay.
you have some questions?
Okay, so hopefully we will see you here in May about.
Okay, we will definitely see. Okay. But Giorgio, do you have questions?
No, thanks. Just, you know, it does make you feel immensely rusty, actually. You know, it's a very good talk. Thank you very much.
Okay. We'll see you.
Bye.
You tell me whether there are covariantly constant.
Hey, I was wondering about that, but yes, it needs thinking, you know, it's a difficult activity. You're right, it's a good question.
Maybe my guess is for extremal black holes, maybe they are there.
Yeah.
I would guess that probably are.
It's also my guess. But
if I find it, then I can immediately prove results for excitations on the boundary of the black hole on the horizon.
oh, I see.
By these techniques, one can easily prove. Okay? But one needs covariantly constant ease.
Covariantly constant field. Oh, okay. I'm going to think about it.
If you have any idea.
Problem.
Okay. All right. We'll see later. Okay. I'll let you know. Okay.
No,
Okay.
sorry, I'm busy with very stupid calculations. Very stupid. Due to incompetence. Ciao.
Okay.
Okay. All right.